So welcome back to another session on the quantum theory of scattering. So next we have to start a partial wave analysis. Okay, so before going to start the partial wave analysis, first we should know about what is meant by partial wave expansion. Okay, so once you are okay with the partial wave expansion, then we can go to the discussion of the partial wave analysis. Okay, so the first task is to discuss what is meant by partial wave expansion. Okay, so in order to get some idea about the partial wave expansion, the first thing we should know about the spherical harmonics. Okay, so spherical harmonics usually will denote by symbol y l m theta phi. Okay, so what is the importance of such spherical harmonics? Okay, so usually the spherical harmonics comes in quantum mechanics when you're dealing the problem of the free particle uh, lying on the surface of a sphere. Okay, so consider a free particle on the surface of a sphere with some radius r. Okay, so the particle is free and it is on the surface of a sphere with radius r. Then what would be its Schrodinger equation? So consider a sphere of radius r and there is a free particle there. There is no force on it. Then according to Schrodinger equation, you can write minus h bar square by 2m del square psi equal E psi. There is no potential here because the particle is free, so the potential is zero. Okay, now what would be the function of psi? So if you expand the del square, okay, so this I can write minus h bar square by 2m. So del square in spherical coordinate system 1 upon r square dou by dou r square dou by dou r plus 1 upon r sin theta, r square sin theta dou by dou theta sin theta dou upon dou theta plus 1 upon r square sin square theta dou square by dou phi square on psi equal E psi. Now, since the particle is lying on the surface, so therefore there will not be any variation of psi with radius. So the dou by dou r of psi would be 0. And so that means the psi would be only function of theta and phi. Okay, so I can write this equation as minus h bar square upon 2m 1 upon, and the radius is capital R, so 1 upon capital R square sin theta dou upon dou theta sin theta dou theta plus 1 upon R square sin square theta dou square by dou phi square acting on psi is a function of theta phi equal to E psi of theta phi. Okay, so this left side is corresponding to energy. Now, if the particle is free, then only energy is kinetic energy, and the kinetic energy I can write in such case kinetic energy I can write L square upon 2mr square. That would be total energy. Okay, so this same thing I can write as L square upon 2mr square acting on psi theta phi equal E psi theta phi. So we can identify the form of L square from comparing these two expressions. Okay, because I can write down in another way as 1 upon 2m r square. This r square can be taken outside commonly into minus h bar square 1 upon sin theta dou by dou theta sin theta dou upon dou theta plus 1 upon sin square theta dou square by dou phi square acting on psi theta phi equal E psi theta phi. Okay, so comparing these two expressions, we can directly identify the form of L square. So the L square, the square of the angular momentum, in differential form, I can write minus h cross square 1 upon sin theta dou by dou theta sin theta dou by dou theta plus 1 upon sin square theta dou square by dou phi square. So this is your L square. Okay. Now the eigen function of L square is what is called the spherical harmonics. So we can write the L square acting on YLM theta phi as the eigenvalue is written as L into L plus 1 h cross square y Lm theta phi. So this YLM theta phi is called spherical harmonics, and they are eigenfunctions of operator L square with eigenvalue L into L plus 1 h cross square. Okay, so then what would be our total Hamiltonian in this case? So total Hamiltonian, we can write simply minus h bar square upon 2m capital R square L square. So therefore the L square commutes with h. So commutation of commutator HL square would be 0. So this implies that the L square is a conserved quantity. L square is conserved. That is, the angular momentum would be conserved. Okay. Now, what is the explicit form of YLM theta phi? The YLM theta phi is slightly big expression for YLM theta phi. YLM theta phi can be written as 1 upon square root of 2 pi, some coefficient CLM, then the associated Legendre function PLM cos theta, then e raised to I m phi. The associated Legendre polynomial is PLM, and we know how to find it. Okay, because this can be defined in terms of the Legendre polynomial. So this PLM cos theta by definition, which is 1 minus cos square theta all raised to mod m by 2 d m by d of cos theta upon m. So mth derivative with respect to cos theta of PL cos theta. So this is the associated Legendre polynomial PLM cos theta, where PL cos theta is called the Legendre polynomial. Okay. So this is Legendre polynomial, and this PLM cos theta is associated Legendre polynomial. And the another thing about the spherical harmonics is its orthogonality condition. So if you integrate YLM over the surface, so YLM theta phi y L prime m prime theta phi over the solid angle gives Dirac delta, delta L L prime, delta MM prime. Okay, so this YLM satisfies the orthogonality condition, or basically the orthonormality condition, and it is a conserved quantity. Okay, so therefore this YLM, it is possible to write any function on the surface of a sphere using this YLM theta phi. Okay, so that means this YLM theta phi can be taken as a basis function to expand functions on a surface of a sphere. Okay, so if you want to express any wave function of the particle on the surface of a sphere, okay, it will be some arbitrary function, and that arbitrary function would be the superposition of, or the sum of, this YLM theta phi. Okay, so any function psi theta phi, is possible that psi theta phi can be written as sum over Lm, some expansion coefficient CLM YLM theta phi. So okay, so this is the mathematical expression of this particular statement. Okay, so this is just a simple revision of the spherical harmonics. That is not enough for to know what is going to be partial wave expansion. Okay, so in order to know the partial wave expansion, so we should take a problem with the particle in a potential. So consider a particle in a potential, and suppose the potential is spherically symmetric. Okay, so consider a particle in a spherically symmetric potential. Okay, so if you connect this to our particular uh, discussion, that is the scattering, then instead of simple particle, we can write the scattering problem in spherically symmetric potential. Okay, so in spherically symmetric potential, the spherical symmetric potential, suppose the originally the potential we can write is V of R. Since spherically symmetric potential, the potential value would be independent on direction. So V of vector R can be simply written as V of modulus of vector R, or I can simply write V of R. So it's spherically symmetric potential means V of vector R can be simply written as V of R. Okay, so if you have a scattering problem with spherically symmetric potential, then what would be the corresponding Schrodinger equation? So our corresponding Schrodinger equation, I can write minus h cross square upon 2 mu del square psi of R plus V of R psi of R times E of psi of R. Okay, so I've already used the assumption that the potential is spherically symmetric. Okay, now how will you write del square? So del square, the form of del square in spherical coordinate system is 1 upon R square dou by dou R square dou by dou R plus 1 upon R square sin theta dou by dou theta sin theta dou by dou theta plus 1 upon R square sin square theta dou square by dou phi square. Okay, so this we can substitute here. Okay, so before substituting, it is possible to rewrite this term in terms of the square of the angular momentum, because we already know that the L square take the form minus h cross square upon 1 by sine theta dou by dou theta sine theta dou by dou theta plus 1 upon sine square theta dou square by dou phi square. Okay, so if you take this r square outside and multiply and divide with minus h bar square, you will get L square. So this del square, it is also possible to write it as 1 upon r square dou by dou r square dou by dou r minus. Okay, so we'll get 1 upon r square here and 1 h cross square inside, and it become L square. So we can write L square by r square h bar square. So this is the form of del square. So therefore my Schrodinger equation can write minus h cross square upon 2 mu 1 upon r square dou by dou r square dou by dou r. Then minus into minus will become plus and become L square by 2 mu r square plus V of r acting on psi of r theta phi equal to the energy of psi of r theta phi. So here we can use the variable separable method. So this psi of r theta phi we can divide into two parts. So r and L of r y Lm theta phi. So then our equation become minus h bar square by 2 mu r square dou by dou r square dou by dou r plus L square divided by 2 mu r square plus V of r and L of r y Lm of theta phi equal energy times r and L of r y Lm theta phi. Okay, so this can be simplified. For the simplification, this gives the expression. Okay, so I am leaving that simplification to you. So this become minus h bar square by 2 mu r square d square by dou by dou r square dou r and L by dou r. Then there will be y Lm outside. Then L square on y Lm we would give L into L plus 1 h cross square r and L y Lm divided by 2 mu r square plus V of r and L y Lm equal to En r and L y Lm. So this y Lm can be cancelled throughout. So this is the radial equation to take the form. Our simplification become minus h bar square by 2 mu d square r and L by dr square plus V of r L into L plus 1 h cross square by 2 mu r square times okay, so there is a small correction here. So d square of r into RNL times r into RNL of r will give En times r into RNL. Okay, so this step I am leaving to you. You can reach from here to the above steps to here. So I'm very sure. Okay, so this you can do as homework. Okay, so you can do it yourself. There is no big deal about it. Okay, so this is your RNL, the radial part. And what about the angular part? So which is L square acting on y lm theta phi would give L into L plus 1 h cross square y lm theta phi. Now it is possible to write any such function, any wave function, so which is psi r theta phi in the form of RNL of r y lm theta phi. Okay, so the hence a general wave function, the psi of r theta phi would be a series expansion, or it would be the superposition of all such possibilities. Okay, so here I have fixed my n. Okay, so if you didn't for a fixed n itself, there can be many possibility for L and M. So hence a general wave function, a general wave function in spherically symmetric scattering can be expanded as psi of r theta phi equal to sum over Lm Alm r and L of r y Lm theta phi. Okay, so this expansion is called the partial wave expansion. That is the expansion of wave function in terms of spherical wave. Okay, so here we expanded the wave function in terms of spherical wave. So such expansion is called partial wave expansion. So it is called partial wave expansion. Okay, so here now we are going to use this particular result in our scattering studies, and that such studies is called the partial wave analysis. Okay, so this is we can put inside the box. So in any spherically symmetric problem, we can use this kind of expansion, and it would be very beneficial in some situations, particularly for the spherically symmetric potential situations. Okay, so it is not spherically symmetric scattering. The wave functions spherically symmetric potentials. Okay, so there is a small mistake here. It's not scattering. For spherical symmetric potential, we can expand the wave function in this particular form. Okay, so with this we're stopping the discussion about what is meant by the partial wave expansion, and the next video we'll discuss about what is exactly the partial wave analysis. Now we can use the partial wave analysis in order to calculate the differential scattering cross section and as well as the total scattering cross section. So that is the main idea behind this the partial wave analysis. Okay, so see you in the next class.